Well,
All right, thank you everybody for coming. Today we have Chenyang. Oh, one from the, what?
but I think it's over there. People turn off everything.
So this. This. Yes, thanks everybody for coming. Today we have Chenyang An, who is a applied scientist at Amazon at AWS, the Automated Reasoning Group. For that, he was at UCSD, in the math department there, doing his PhD. And yeah, take it away. Thank you.
Thank you, Emily. Yeah, so I'm a applied scientist at Amazon. My background starts with math PhD, working in studying algebraic geometry, mathematical string theory, those kind of things, for the first 3 years of my PhD. And then I see lean, I see NLP, I see why shouldn't we try that, right? And then I switch to doing language model reasoning in natural and formal language. I mostly focus on post-training for improving model reasoning ability for my last 2 years of my PhD. And then I joined Amazon as applied scientist working in the automated reasoning group. And that is my background. Great. Today I'm going to give a talk on one of the methods for improving reinforcement learning for language model reasoning. Great. So can I just have an estimate for the background of the people here? How many of the people here knows like what is fine-tuning? If you know, just raise your hand.
Actually, I don't know the difference between fine-tuning and reinforcement.
Okay, cool. And then language model, does people know what's that? Like, okay, got it. All right, cool. So yeah, so I'll give some details as far as I can. But please raise your hand if you have any questions regarding anything I talk about. I know it's like a very disciplinary area. So people from all different backgrounds know different kinds of knowledge, and let's just discuss. All right, cool. So so yeah, so my agenda. First, I'll just give a formal introduction, like a very light introduction to what is the large language model reasoning task nowadays people work on. And then we're going to talk about some problems with standard reinforced learning, like what's the problem with that. And then we're going to talk about existing method to strengthen reinforced learning training lightly. And I'm going to talk specifically about my method. It's a method I come up with that I think would help. And this work is in submission. And that's it. Right. Cool. All right. So it's a very obvious two different kinds of reasoning tasks that people use nowadays in language model reasoning area. This is what OpenAI are doing, what Claude are doing, what they're competing against each other. And there are two kinds of tasks. The first one is the boxed answer task, which is that you have a problem statement, and then the model is expected to give a reasoning trace. And most importantly, there's the final answer that exists in the box, like an integer or a symbolic form or whatever, so that we can use that to check your model output against the ground truth. Okay, and then this would be an example, and this 10 would be the final answer on this. All right, and the second kind of task would be maybe people are more familiar with here, which is the lean proving task, right? Well, not necessarily to lean, but all different kinds of programming language exist to do this kind of checking. But again, this is example in lean. We have theorem statement, and then we have several proving steps regarding that. And then lean is going to tell you whether this proof is correct or not correct, to put it in a simple way. And then the model is expected to be given the statement and output the proving steps. And then we're going to check whether model output satisfy the lean checker. Does that make sense? Okay, sounds familiar. Cool. So but I would say like people focus on this kind of thing mostly nowadays. not because this is not full, this is super cool. It's just, more people know about this kind of things. Competition, high school competition, undergrad, level math problems with an integer answer, like they know these kind of things naturally, but they're not familiar with that. But you can see like, literature or people are getting more and more interested in this kind of thing nowadays, for sure. And I'm pretty sure everyone here knows this trend, right? Cool. So, all right, so very light introduction to reinforced learning. So basically, a language model is rewarded, all right, based on two criterion. For the box answer task, if the final answer is correct, obviously, right? We're gonna only check the final answer. And the second signal for the proof generation task by Lean, Rock, whatever, right? The proof is checked by the proof assistant. Then we reward the model. Otherwise, we don't reward the model because model is doing something wrong. All right, and this is nothing but a very, very like simple math objective to optimize against, which is that we want to use gradient to change the model parameter so that model would output reasoning traces and final answers such that they can get rewarded. I mean, it's just maximize something against a ground truth through the parameters. Yes.
Good question. How good is the proof assistant here? So if they check a proof and they turn that it has no problem, and we like 100% trust that.
Yes, that's the key thing. We can 100% trust it. And we have even very, very hard. So by first it's proved, like it's sound, meaning that theoretically we can trust it. So it's proved. And second, in practice, we have very hard math theorems that's with very long proofs that are checked in the system. So it's actually working in research math level, right? On the research level, math level.
Formal statement is given as part of the input.
Yes.
It doesn't have to translate the statement to Lean itself.
Uh,
Then you can't trust that it translated correctly.
Yeah, sure. But yeah, you have to first make sure that the formal statement, so the problem statement is correct. That part is not checked by anyway. Only human can make sure that, right? But once you have the right theorem statement for all the proofs, once it passed the checker, you get absolutely trusted, right?
But trusted means like it's the ground truth, or is trusted by meaning that it's the only thing we can trust.
No, it's ground truth, so it's 100% logically correct, right? It's not like it's the best we can do, but it's mathematically correct, right? Yeah. Okay.
This term ground truth a lot lately.
Yeah.
What is it and why is it useful?
Yeah, so the ground truth simply mean, yeah, ground truth just simply means the correct answer.
But why ground? Where's where?
Yeah, so
Is there
basically,
higher levels of truth that are not ground?
yeah, so ground truth are used in two ways. First, when you're measuring model, you're measuring model performance, you're testing model, right? In that case, you're gonna measure model output and the ground truth. So basically like grading, right? You're gonna see whether model output is the same as the ground truth. If not, we say it's wrong. On the other hand, if it's during training, then we compare model output and the ground truth one way, all right? Comparing model output and the ground truth and see, are they the same? If they're the same, then we encourage model doing this. So that's basically how ground truth is used here. Yes?
Yeah, I have a question about this ground truth term you can apply to these proof checkers. So like technically you can have a bug in your proof assistant, whoever wrote the proof assistant.
Sure.
So like technically, is that not the ground truth?
Yes,
Because you have to verify your proof assistant's correct. And there's always-
absolutely. It's, yeah, it can go, but yeah, you're right. Yes.
So the kernel of these groups, it's only like a few hundred lines. So we've had a lot of eyes on these to have this sort of confidence that there's not a bug.
Yeah, yeah.
Also, I think the ground truth a lot of times can be, there's like a human written ground truth that people are comparing against, like, let's say a packet written proof on Maclet. So there's many ways to do the proof, but somebody did it this way, so maybe you're comparing just against that, but if you come up with a different proof and it goes through the checker, that's also fine.
Because you don't know if the chips that it's running on don't have a bug. You can go all the way down.
Yeah, that's totally right. Yeah, that's right. Yeah. So, okay, so now it gets to the juicy part. So the problem is that, what's the problem with the standard RL? The first kind of problem is that the reward is sparse, right? So think about if you ask the model to prove the Foreman's last theorem, model can never prove it, right? It can never prove it, it's never going to be rewarded. If it's never going to be rewarded, then there is no reason why we tuning model on this problem. Okay, so that's the first big problem. The word is sparse. A lot of work is trying to address that. Yeah, that's one thing. The second thing, the training is unstable compared to other like supervised fine tuning. Because reinforcement learning, there are a lot of parameters you can tune, and the model can get collapsed during training. That's more engineering side of the things, but that's also a problem people try to address. And then the third thing would be yeah, so once the model is rewarded in a particular way, right, then it's gonna commit to that path. So that's also a problem. And this is one of the thing that my method trying to address. And the fourth one is again, it's a recent discovery. It's very new. Is that people discovered that reinforcement learning, standard reinforcement learning, they only improve model passive one performance, meaning that model is only allowed to output one try to give one try to a problem. Okay, and then we measure its performance. Whereas passive K, which means that model can attempt K different try at a given problem. Okay, whereas the reinforcement learning does not improve passive K performance when K is large. Yes.
Sorry, just a naive question. So wouldn't that be remedied by giving the model a reward when it attempts the solution K times? And if any one of those solutions is correct, give it the reward. Wouldn't that improve pass at K performance through reinforcement learning?
So if you so first, no, people discover if you do that, maybe this is one of the places would come up, because you let model generate a lot of things, right? And then you reward the model for the particular one it succeed. So the model will commit to that succeed path, and that's it, right?
But
So,
if we don't tell the model, we're giving you a reward for trial number 3,
Yes,
but we're just giving you a reward for
everything you try.
everything, then the
Yeah.
model is going to commit to everything.
Yes.
Those 32 things that it tried,
Yeah,
and then it's going to keep trying those 32 things every time,
yeah.
instead of just trying technique number 3.
So basically, you're trying to reward model not only on the correct path, but also on the failed path, like the false one, right?
Right.
But then you're encouraging model to do the wrong thing.
But as long as the correct path is contained within those 32 trials, that's still fine, right? If the model tries 32 things,
Yeah,
and it gets the reward when at least one of those is correct, then the model can keep trying those 32 things. And as long as the model tries those 32 things each time, it still gets through. It's going to commit to all 32 ways, including the correct way.
right. But then why don't we, like, because all the besides that 3 correct ones, all the rest are wrong, right? But why do we encourage that
I'm just
after all?
trying to like improve this because
Mhm.
if we just reward the model for the correct way,
Yes,
it's going to overcommit to that one way.
yes,
But if we reward the model for a lot of ways, then
Yes.
that problem goes away. That's what I was trying to.
so basically, I think you're risking that this passive K is not improved, but also this passive Y is also not improved. It might be that case, but we can discuss afterward. Let's keep moving, right? Yeah. Okay, so existing methods to strengthen RL or whatever people find that's going to be very useful for improving RL results. All right. First and most importantly, you need to start RL with a better pre-trained model. So that's the single most important thing that people discover. So you need to have a very strong model. The model should already knows a lot of different knowledge, but probably it's performing bad on reasoning for now because it don't know how to use the knowledge it already knows. Okay. And in that case, if it's very strong, then if you do RL on that, the model would have a very strong result with RL. And that's experimentally proved in literature. Like not only literature, but the big companies test it out, right? And then the second thing would be prepare high quality RL training data sets with the format with non-sparse rework. So that's also easy to understand, right? You need to have more data. That's also the second most, that's the single most important lesson people learned for the entire generative AI era. more data means better better model, better performance, and everything, right? And then also people discover different things to increase training stability. You use clipping methods. You try to make your algorithms more stable through clipping, through different kinds of ways, right? And then in order to address the sparse reward problem, people, for example, you develop a lot of different process reward thing, which means that you're not only rewarding model on the final output, you're also rewarding the model on the middle steps as well. So that in this way, the model can get rewarded for providing the right middle steps, but failing on the final answer. Okay, there are a lot of trials on that. Great. Yeah, and the final one is final set of things is that we're trying to encourage the model to explore more different solution space. Okay, encouraging model diversity basically, and there are different ways to do that. For example, you can add a entropy parameter in the loss function. You can use reward kinds of things to encourage model to do that, or you can use very complex search methods. Lots of agent works focus on that, but there are a lot of different ways to do it. Yes. But again, I would say people discover this is the most important thing for sure. Prepare a better pre-trained model. Okay, so let's go to the method I'm gonna talk about today specifically. The inspiration here is that math theorems can admit distinct proof, right? So this is an obvious example, but the examples are like there are millions of examples. Let's look at the prime number theorem. All right, there's an elementary kinds of proof, which only use real numbers, which only use elementary tools in inequalities, combinatorials, arithmetic estimates. Whereas there's a second proof, which is earlier than the elementary proof, which use complex analysis and combinatorial estimates, Riemann zeta function. And that would be very different from the elementary proof for sure. Different intuitions, different insights, different tools. Yeah, you name it, right? It's like really different to proof. So so the problem is that given a math theorem, different proofs may use different intuition, different tools, and different insights. And can we let a large language model to learn to provide multiple distinct proofs for a given theorem? And the benefit is that the diversity among all those different proofs are very high, right? And this would be be ideally what the model need to learn when it's doing its explorations for math reasoning tasks. It should be able to go from all different perspectives with respect to a theorem, right? Yes.
Control, just you ask it to do a proof by contradiction, that sets off a different class.
Yeah,
You ask it to give a direct proof.
Yeah. So that's that thinking would be like fixing a model, right? We fix a model, we don't talk about its training. All right. And how do we let the model to tackle a problem in different ways? Right. So that's one mindset. And the other mindset is, okay, we have a model, we can train this. How can we train this better to explore different math theorems? Yeah. Right. And then
This idea is to improve the third point is that you brought up, that it can learn to do things only in one specific way, and so that's why you want to address.
yeah, that's right. I don't want model to overcommit to any particular path during the reinforced learning stage, right? So so here's the idea. So let's talk about for the box answer problem first. First we let the large language model to work it to provide any reasoning trace it can. And then we collect and we summarize those training traces. And then we're gonna say, hey, model, all right, this is a summary of the proof that you shouldn't use to do this problem. You should try to do this problem in a different way to that. Okay, and the model should be able to the model is asked to do that. And then most importantly, after the model generate a second proof, all right, we're going to use a LMS judge to check whether the two proofs are essentially same or not. The first proof and the second proof, are they the same or not?
So here you're using the
Yeah.
word proof, but you're talking about the box answer problem.
Yeah, that's right. So reasoning traces would be a better word here. Yeah, reasoning traces, correct. So yeah, so basically we're going to use LMS judge to check whether the current reasoning trace uses the same method as its previous reasoning trace. And importantly, we're going to reward the model if both the final answer is correct and the LMS judge think that two reasoning traces are different. Okay, we ask for two different criterion, both satisfied to reward the model. Okay, and then the experiment is performed on the math data benchmark for this set of things. So this is a picture we're gonna see. So this is standard RL baseline, which is that model is given the problem, and then the model is gonna give the COT the final answer, and it's gonna be rewarded based on the final answer only. So that's the standard ones, okay? Whereas I'm saying that, okay, so we should do that, that's fine, but also we should do things in extra to that, in addition to that, which is that we're gonna summarize the proof. Okay, we're gonna ask the model to solve the problem differently from the proof plan. And there's an LMS judge, LLM judge to check whether the COT is different from the previous COT. And then we're gonna reward based on the correctness and the diversity. Yes,
So is the judge a human?
the judge is another language model.
It's another language.
That's right. Yes.
That was to mention your question.
Yeah.
What is the reward for?
The reward for the LM is that is basically so how can I say that? So if the LM output is the same as let's put it in a vague way, what we want, for example, the final answer is agrees with the ground truth. Okay, then we're gonna encourage the model to keep doing whatever it's
How do
doing.
you do that? How do you encourage?
Yeah, so basically we're going to use gradient descent, which means that we're gonna calculate the gradient that the model can produce this, that the model is producing this final answer. We're gonna maximize that so that there's a gradient direction, right? And then we're gonna add this gradient to the model parameter. So that's actually the gradient descent that's underlying all the language model training. So this is exactly people use everywhere, right? Right, so yes.
Yeah, so my question is more about the report, like the already have on here. So the reward algorithm, you're gonna reward a model if and only the answer, the two answers are different. And they are both correct.
Right.
How are you gonna measure the difference? Like, if it might be the same, very similar chain of thought, only maybe one more step or something like that.
That's
So
right.
another model job, you verify that as they are different, but if a human job, you verify that maybe that, you know, like matter difference.
So basically, you're saying that language model judge is cannot like it cannot really differentiate two different
Like,
proofs.
basically, what's your prompt for that? Make
Yeah,
sure
I'm gonna
that-
show the prompt, right? Yes.
Yeah, Senos says, is the reward one, outputting a binary value?
The binary what?
Yeah, 0 or 1, the reward.
The reward is 0, 1, right? Yes.
So why not use something like a distance-based reward?
Yeah, it can, right? But the thing here is to prove that this actually helped. But how to optimize this entire thing, it's not investigated, right? But yes, I agree. Yeah, why not, right? Maybe we can develop a great distance function that can measure exactly how two proofs differ, right? Maybe we can do this in a very systematic way. Maybe we can quantify like a geometric proof and an algebraic proof, how different they are, right? These are all the questions we can study, right? Yeah.
And,
Now,
yeah, say, what is like, how do you verify that the LLM judge is doing its job correctly?
we don't know, because if you ask a human to watch this, it's not scalable, right? But after all, if this method helped, then on the final benchmark, the model performance, the model that's being trained with the orange plus the blue one should perform better than the model trained only on the blue Python, right? And that's the final verdict. You're gonna say, hey, this method worked, right? Yeah.
If your questions, there are only one answer. That doesn't exist another, solver.
Yeah, it's okay, then we just don't reword it, like. Yeah, the model, yeah, right, the model is not rewarded,
But if you
right?
apply the
Yeah.
orange pipeline of that, would that decrease the order of, what is, emphasizing more exploration, but there's no need for exploration.
That's right, it could be the case, right, yes.
What kind of problem only has one way? Solve problem,
So 1+1.
like, think of at least a dozen.
Yeah, that's a great observation. Yes.
Like there's, intermediate reasoning, maybe it has some mistakes, we're saying that, ends that like, if the performance is going up, then it's okay. But what if in the intermediate steps, like there are mistakes and the judge is not, correctly, finding it out? But, in that case, isn't that going to, corrupt the word model somehow?
Yes, so to address that question, first, it's very valid concern. It's the first thing we worry about when we conduct experiment. Because, so basically, let me rephrase the question. So basically, during the first round, right, the model is already rewarded for producing the correct answer, right? So basically, the model already know how to do this problem, in short, okay? And then if we ask to do this problem again, all right, the model, it's possible, absolutely possible, the model is gonna give some rubbish, and then the correct final answer. All right, that's totally possible. So to answer that question first, we try to make sure that in this, and then there's even easier to corrupt this, which is that in this proof summary, there's final answer. So the model already knows the final answer through the prompt, right? So first, we try to ensure this doesn't happen for the summary part. We don't give any integer during this, in the summary. We clearly instruct the model not to contain anything, like trying to only capture the proof plan, but not giving any detail, but that's one thing. And the second thing I think I want to say is that think about the 4 digits by 4 digits multiplication problem. Okay, Sultan model cannot do that without a very specific chain of thought, which means that it knows how to do it. But if you directly prompt it to solve it, it gives false answer. Right, so it means that for the final answer, the middle step, the final answer is very sensitive to the middle steps. That's my practical observation for this thing. Right. But what you said is valid, and it can happen. Right. But again, I want to say the final verdict would be the model trained with everything having a better performance than the model trained only with the standard RL. This will show that this pipeline is working or is helpful. Right.
Steps. So that we can make sure that we'll find
Absolutely, like, okay, so because this is for the final box answer task, right? But once it goes to proof generation task verified in link, then there is no such problem, right? Because all the chain of thought should have to be right in this way. Yeah, so your concern exists for the box answer one, but doesn't exist in the proof generation case. Right, yeah. Okay, so, all right, so the key assumptions behind my method is that first, it's very hard to generate the reasoning trace in the final answer correctly. If it's very easy, why training the model? Just let the model do the problem, don't train it. Everything is fine, it is solved. So that's the first assumption. The second assumption, it is relatively easier than generate the answer, but still very hard to check the validity of a given reasoning trace in the final answer. Because if it's very easy to directly check the answer, all right, then we can use that as a signal to train the model. And then the problem is also solved. Okay, so these two are very hard. But the third thing is that it is easy to summarize the proof technique used in a reasoning trace without caring about validity. So because here, what it's doing is just summarize the proof, right? And fourth, most importantly, it is easy to check if a given proof techniques is used in a reasoning trace without caring about its validity. So basically, I'm exploiting that these two are easy, so that my LMS judge can work in this judging task. right? This LMS judge is not tasked with verify the answer directly or COT directly. It's very hard. And there's no such great model for free, because if there is, OpenAI can train the best model already to solve anything. But if it's only used to check the proof technique, only used to see if you use, let's say, Riemann zeta function here, right? Maybe you rename it, it's okay. But if you actually use the Riemann zeta function, then the model can complain. That's important, right? So that's the key assumptions here. Okay, and then it's the actual LM prompt. The first one is the original RL prompt. So basically it's count top. So, okay, first I want to say, I want to, test this method on really hard problems, right? Algebraic geometry, number theory, and then see geometric intuition, algebraic intuition, all those kind of things. I like it. It's not gonna work because all I can do is a 7B model. And therefore, the benchmark we're using is math, MATH, which is of high school, more advanced side of the high school problems. All right. And this is an example of the problem. So let's say, let's see. So we're gonna count how many whole numbers divide 50 without a remainder. All right. And if you directly prompt the model to do that, the model is going to enumerate, which I think it's a totally valid method to do that. And now we're going to use a different prompt to instruct the model to do that. And the model, so basically we're going to say, hey, look, this is the problem. All right. But you cannot enumerate, basically. All right, do this again. And in this way, models can give you something different, which is factorization, count exponents, and multiply. Right, a different way to do that. Right. Again, it's a trivial example. In my experimental constraint, that's all I can do. But ideally, I want it to be number theory, right? Hard stuff. Right, that'll be very interesting. And this is the LMS judge prompt. So basically, your careful math teacher, I'll give you the problem statement, the solution of the student, and a proof plan. The student has been taught with the proof plan, and if he's instructed to, and he is instructed to find a method that is very different from the proof plan. And I want you to carefully check if the solution is very similar to the proof plan. And I give it the proof plan, the student solution, and the model should output yes or no, basically. Right. And the first one is how do we generate the summary of the proof? All right. Basically, I asked the model to summarize the solution of the problem in short sentences, and ask if no number can be shown in the summary, and don't give out the final answer. All right. Cool. Yeah. Okay, and that's for the boxed answer part of the story. Okay, and then remember we have a second task, which is proof generation task for language model reasoning. And in this case, I would say we're better positioned because the reward hacking or information leak cannot happen in this case, right? Information leak can also happen, but reward hacking doesn't happen in this case. And then, and in this case, all right, we're gonna first let model prove the theorem without any restrictions. And then we're gonna ask the model to prove the theorem without using search-based tactic. In Ling, those include like linear, simp, ring, ESOP, and linear, omega, trivial possibility. Like, okay, so this is one thing I want to complain, which is that currently when model is doing Ling proof on the popular Ling benchmarks, they're heavily using those tactics. And those tactics, they don't contain a lot of math intuition in that at all, because they are basically search heuristics tactics, which means that if the model uses tactics and there's behind on the back end an algorithm to search the proof for this a theorem, try a lot of combinations or whatever. And then if this theorem is simple enough, then the search heuristics will find a proof for this. So basically, this is like the hand wavy in mathematicians language, right? Okay, it's easy, right? Or something like obvious. right?
You can report the trace.
Yeah, you can report the trace, but that trace is never included in the model training or whatever. So basically model is, when it's being trained on proving Lin theorems, what is being asked, what it learns is that, okay, this is a theorem, right? I should apply simp here. I have no idea why I should apply simp here, but I should apply simp here because I don't know, because it's going to be solving the problem. And the model see that it can use simp to solve a lot of different kinds of problems. So that the model learns that simp is really powerful, right? But it doesn't really know how simp solve anything. So simp
What's
just solve.
like linear and range, I would think you would want, if you, LLMs can recognize, I have a system of linear inequalities. This is exactly what linear, there's a theorem that linear will solve every linear inequality if it's solvable.
Yeah, that could be the case. Right, I think these are the tools that model can use, not saying it cannot, right? But I'm saying that the model should be forced to really know what's behind the thing, right? If you use
ASAP, nobody knows what's, you know, at least I don't know.
like this sim, it's really like you have a list of all different kinds of tactics. The model is the algorithm is trying one by one, and the content of sim is changing all the days because people update the list all the time. So basically, the what's really going on behind the sim is changing all the time. But the model learns this in a specific through a specific training period. So yeah, so
Some confusion.
yeah.
In my understanding was we were trying to produce a new model.
Yeah.
You have your large language model, you're using it fine, but the goal is to train an alternative.
Yes.
So if you have been, the way, but now that we described it was how people have already trained the model rather than how you could train it. Right? And I think Alex's point is that after it's done the proof by using sim, right? You can you should be able to unfold that and see exactly what step we do, right?
There's a sim question mark that will pull out the theorems we follow.
Yeah, you can
So
like
So
basically,
you do have access to that.
yeah.
But you don't want to use that in your training. Is that what you're saying?
So, okay, so one way to approach it is that, okay, you're gonna say, once I use sim to construct the proof term, I'm gonna extract the proof term out and then train the model on this proof term. Yeah, that's working. I think that's gonna work. But first, few people use proof term to train model nowadays, like,
We're talking about you. what
yeah,
you do.
okay, yeah, of course. So, again, what,
Proof term,
Yeah.
it's a term and not a tactic.
not a tech,
That's what you're saying.
yeah,
It's like, you're trying to learn how to do Python, but you're gonna read assembly.
Okay,
Yeah,
I
it's
understand, but
You can apply it, but,
You can apply proof terms, yeah, but then you sort of have to learn two things, you have to learn assembly and Python. And in the middle of Python, call assembly.
That's all.
Right,
Maybe you can.
maybe you can.
yeah.
I found supposed to see before it.
But yeah, I understand the concern. You're saying that there's a better way for a model to learn this, right?
I'm not saying, I'm.
Yeah, maybe there's a better way to train, to like overcome the defect I just talked about. For example, extracting the proof term and train the model on that. Yeah, I totally agree. But in this work, I'm trying to show that my method works better than existing ones.
Okay, yeah.
So of course,
They're
there,
not part of your method, that's all you're saying.
yeah, right, yes, but I totally agree, and I think it's a good idea, like, it could be a good idea, because proof term contains more information, maybe, right? But yeah, sure, so basically I'm saying that model, hey, I'm gonna penalize you if you use any of them, so that you are, asked to fill in all the proving details yourself without cheating, okay, without cheating, right? So that's how I, do this problem. Right, so this would give a summary to my method on the two different language model reasoning tasks. Right, compared to the standard reinforcement learning, right? Okay, and at this point, I should emphasize that this entire thing I'm talking about, that this the problem with reinforcement learning, the problem about the diversity of the reinforcement learning, these are like under heavy investigation recently. And there are a lot of literature coming out regarding this. Actually, this is one of the hottest topic right now in language model post-training area. And yeah, so this is an important problem. Yes.
So when you ask the model to write proof and you're not allowing it to use these tactics, can it still quote lemmas or theorems from MATLAB?
Yeah. Yeah.
So isn't that also not forcing the model to really know how, I mean, you can always code a big enough or a powerful enough theorem to sort of.
So basically, you can write any of your tactic. You can write a tactic that means actually anything, right? So technically, I would say yes, but okay, my experiments, personal experiments shows that these are the worst among all the tactics that really corrupting models, all the proofs. Like if you ask the model to produce a proof, then I would say 60 to 70% of the time it includes one of these. Right.
Sure, I mean, so
Yeah.
what if you like just for the simpler problems, what if you just force the model to not use theorems from MATLAB and just use calc blocks? Do you think that's going to further improve performance, in which the model really has to calculate everything?
Yeah, I think so. Right, I think so. I do think so. Right. Yeah.
I think part of what is scary about this is that I don't think I've written a single proof in Lin that does not use something like that.
Yeah, sure, absolutely. Right. And I think especially during training, I mean, during test time, I don't have any problem with that because model proved the thing, right? But during training, I think it's actually reducing models opportunity to actually learn the math details behind the proof. That's my general assumption here, right? Okay, so let's talk about one of the things that really makes me start to think about this problem, all right? So this is actually a equation that gives you a very cool combinatorial number. And the theorem goes like, we're trying to count the number of the lines on a generic complex projected hypersurface exists in a complex projected plane, projective space. So you don't need to know any of that. You only need to know that we're trying to count number of lines on geometric objects. That's it. All right. And this formula holds true for all the n. Okay. So basically you can change the n here, and here, and the formula always holds. And all of these three different things are very easy to compute. Okay, it's not a black box. Any of these three, it's just a function, easy to compute, absolutely computable in rational closed form. All right. And here's the source. I'm not making this up. So there exists such an equation. All right. And then, so if you really think deep about this problem, okay, for each n, actually, there might exist a very particular proof that can only prove this n case. For example, how people come up with the formula, right? They initially they had no idea. So basically, the first proof the n equals to 3 case, using the cubic, like it's a cubic surfacing complex projective space. And then they proved the n equals to 4 case. And then they use very different method to tackle n equals to 3 and n equals to 4 case. Very different proofs. All right. And then more cases are proved individually until people find a way to generalize this problem with strong enough tool to prove that in its full form. Okay. Now, what happens if the model already know this theorem, right? And I'm gonna ask the model, hey, prove for me, for example, when n equals to 3, what is the number? What the model would do, the model would simply use this theorem and say, hey, you just plug it into this big formula and you're done. Here are the PDF proof. It's probably 100 page. Okay, it's done. Yeah, that could count a proof. But if I ask the model, you can't basically can't use this proof. All right, you have to figure out something yourself. Okay, and then we already know that for many of those individual number, there might exist another different proof, very, very different from the general proof or whatever proof. Okay? And then the model will have a chance to explore a bigger solution space when it's asked not, when it is asked not to use this proof. And guess what? For each integer n, this is a solid theorem. Okay, so suddenly we have a lot of different problems with high quality theorem and the final boxed answer. Okay, such that we can just let the model to search for the middle reasoning traces. Okay, so that's initially why I think this is a very interesting thing to try. Because in this way, we have a lot of high quality reinforcement learning training data with the final boxed answer. Remember, OpenAI or Claude, they're spending a lot of money just to let the expert curate this kind of data. Okay, a problem and a correct final answer. They spend a lot of money on this. So maybe there's a potential to apply this method, and then we can get a lot of high quality reinforcement learning training data. Yeah. So
But can the AI prove it?
the AI prove what?
Can it prove the formula for n equals 3?
This is a standard algebraic geometry
Yeah,
problem
But
that
can the
appears.
AI do it?
I think it can. I mean, because the proof appears so many times, we can even try now, but I think it can.
But it hasn't been formalized clean. Can it find the proof?
Oh, no, it can't. Right. It's, I don't think so, no. But what I'm talking about here is boxed answer problem, which is not lean. It's natural language formulation. Right, right.
Have you tried more evidence of this?
I can't because 7B model cannot solve this for sure. And yes, and only large model can have a chance to tackle this kind of problem, especially under training. And it's big companies game. Like that's one important thing, which is that in academia, if you want to do this reasoning thing, then all you can do is play with 7B model. And the reviewer is going to say 7B is not enough. I want to see, does your method scale up to 70B? And you don't have the resource. Well, so if you're at the company only wants you to use the resource to do the product. Yeah.
And they're Amazon's not interested in them.
Well, I'm not hired for this.